So, welcome to our physics project part 3 by Iwe and Finn. So, I'm going to analyze the vertical motion first, and let's play the video first. All right. So, from 0 to 0.6 seconds, which is where it really matters because of the launch from Finn. As Finn launches the ball upwards, the position time graph displays the positive acceleration because the velocity is constantly changing in the positive direction. As can be seen in the graph, these points are accelerating positively. And the line of best fit is a quadratic line of best fit because between any 2 points, the velocity is constantly changing. So between these points, the velocity is almost doubling up, you can say. So it makes it possesses a positive acceleration. This is also shown in the velocity time graph as before 0.6 seconds as the velocity increases as time goes on. So before this point, the velocity is constantly accelerating. So the acceleration displayed in the video from 0.2 to 0.6 seconds is when the slope of the position time graph and the velocity time graph significantly increases. This demonstrates the ball's velocity after being released from Finn's hand, and the acceleration is around 8.5 meter per second squared according to the graph slope. So our force diagram, since we're only throwing the ball upwards, the force diagram will only have two types of forces. So going up would be the applied force as Finn launches the ball upwards, and the force of gravity pulling the ball downwards. So calculations of F net. So we know that mass of the basketball is around 0.6 kilograms. Therefore, we just plug it into the formula. So we know that F net is equal to ma, which is mass times acceleration. Our mass is 0.6, which is our basketball, and our acceleration is 8.5, explained in the previous slide. And we get our net force of 4.8 newtons upwards. Sorry. So calculations for the force of gravity and the applied force. So we know that the force of gravity is equal to mass times gravity. Our mass is 0.6 and the force of gravity on Earth is 9.81. And we get 5.9 newtons downwards. So F net is equal to Fa minus Fg. So we found that F net and we found Fg. So our F net was 4.8 and our Fg was 5.9 newtons. So we just add it to get 10.7 newtons.
The initial description of the motion. In this motion, the ball is accelerating in a positive direction as it is being launched out of my hand. The ball is only moving left horizontally toward the origin because there's no vertical motion due to the applied force only being in the left horizontal direction. Now for the graph analysis. So the graph description. The piston time graph shows the velocity of the basketball at any given time during the 0.4 second interval of the ball is being launched out of my hand. The graph has a negative slope as the ball is moving towards the origin or in a negative direction. It's actually seen as if the velocity of the ball is decreasing. However, the ball is actually increasing in velocity in the negative direction. So now for the velocity time graph. The velocity time graph of the basketball over the 0.4 second interval. There's a decreasing velocity over time or a negative acceleration. However, just like in the positive piston time graph, the ball is actually accelerating in a negative direction. We can find the acceleration by calculating the slope of the graph on Vernier. And the slope of the graph is 12.6 meters per second squared is acceleration. Now for the free body diagram or the force diagram of the motion. As always, we have our force of gravity and our normal force. This is because my hand is holding the ball against the force of gravity. These two cancel each other out. And then we have our applied force from the left direction as I push the ball towards the left horizontally. the acceleration of the graph, or of the motion. The acceleration can be calculated as the slope of the velocity time graph. And the slope is 12.6 meters per second squared, and the acceleration of the motion is 12.6 meters per second squared towards the left. The applied force and the net force calculations. The net force is calculated as the mass times acceleration. The mass of the basketball is 0.6 kilograms. The acceleration has calculated on the slope of the velocity time graph is 12.6 meters per second squared. This means that the net force is 7.6 newtons when we do the calculation. The net force is also equal to force applied minus force of friction. However, in this case, since the ball is being launched in the air, there's no force of friction. The applied force is equal to the net force, meaning 7.6 newtons is our applied force as well as our net force. It's important to also keep in mind that the force of gravity and the normal force cancel each other out as the ball is only moving in a horizontal direction.
So now we're doing the projectile motion of the basketball. And this is the motion in the upwards and left direction. So the initial description of the motion. So in this motion, we can see the ball is accelerating in the positive direction toward the origin and it's traveling left and upwards. Due to the applied force, the ball is accelerating in a positive upwards direction, but it's also negative downwards because the ball is traveling towards the origin. So now to analyze our graphs. In the position time graph on the top, the y position is increasing because it is traveling away from the x-axis, while the x position is decreasing, as we can see here, because it is traveling towards the y-axis. Also, around 0.5 seconds, the numbers of both these values increase and decrease. One increases and the other one decreases, as we can see. This is due to the applied force as the ball is let go at the very end. But that is not the part we will be analyzing. So now in the velocity time graph, in around 0.7 seconds, the ball accelerates positively because the curve of best fit of the section is quadratic, as we can see up in this motion here. Meaning the ball multiplies in velocity over time, and that shows our acceleration. In the x velocity time graph, the acceleration is negative, as we can see, because the ball is accelerating towards the origin in this case.
Now for the free body diagram, or force diagram of our projectile motion. In the free body diagram, we can see that there's a force applied towards the left and a force applied in upwards direction. This is because the ball is moving in an upwards and left direction, or on almost a 45-degree angle. There's also the force of gravity, as always, as the force is acting downward on the ball.
Okay, so for the acceleration, we used the acceleration equation, which is a equals v2 minus v1 over t, and we got the acceleration upwards is equal to 9 meters per second squared. And for horizontally, we used the same equation, and we got that a is equal to 7 meters per second squared going left. So then we use the Pythagorean theorem. We know that going left is 7, going up is 9, and the hypotenuse is x. So then we found the x is equal to 11.3 meters per second squared. So after we found the acceleration, we're going to calculate the net force and the applied force. So after we do the acceleration, we are supposed to calculate the net force and the applied force. So first we separated it into two different directions. So we're doing the vertical one first. We know that the acceleration vertically is 9 meters per second upwards. And we know the F net is equal to FA minus FG. So we rearranged it to FA equal to F net plus FG. So we know that F net is also equal to MA, and FG is also equals to MG. So we just plug in the numbers and we get the F applied force of 11.3 newtons upwards. So horizontally, since we're doing this project without friction, with friction, it will be F net equals FA minus FF. However, the project does not have friction. Therefore, the F net would just equal to the applied force, which is 4.2 newtons. And so we combined it. I used a little bit of Pythagoras theorem. So basically, vertically, the ball travels, the applied force vertically was 11.3 newtons upwards, right here, 11.3. And vertically, it's 4.2 newtons to the left. So we're finding this dashed lines right here. I denoted it as x. So we know that x squared is equal to the opposite over the adjacent. So which is, so we know that x is equal to 11.3 squared plus 4.2 squared. We got the roughly answer of 12.0 newtons going left and up. So now we found out the direction. Now we found out the force applied in that direction. We need to find the direction. So I use cosine. So I have the dashed lines of 12, what we just calculated, and going left is 4.2 newtons. So basically, I did cosine theta equals to adjacent over hypotenuse, which I got roughly around 69.9 degrees, which I just rounded to 70. So our FA, our applied force, is equal to 12 newtons north, 20 degrees west. That is our presentation, and thank you for watching.